The effectiveness of spray painting, fuel injection, surface coating applications, etc. depends on how well or how poorly microscale droplets spread on a solid surfaces. Another application where the study of this phenomena proves especially helpful is the large-scale geological sequestration of supercritical or liquid-like carbon dioxide in deep porous aquifers in an effort to combat global climate change. Regardless of which application we consider, measuring the instantaneous contact angle is key to understanding the wetting characteristics and spreading behavior of these various liquid droplets on chemically treated and/or naturally occurring substrates such as porous rock. Generally speaking, the contact angle is a function of the interfacial tension of the three phases in drop spreading, namely liquid gas, and solid liquid. The interplay between these interfacial tensions and their subsequent influence on the contact angle can be represented by an equation known as the Young's equation. The early stage of spreading is difficult to analyze since the time scales involved are very short. In my research, I focus on analyzing the effects of pressure on the first few milliseconds of spreading with the advancement of the contact line. During the initial stage, spreading is driven by capillarity and opposed by inertial force. To execute my analysis, I conduct my experiments in a high-pressure drop-shape analyzer that utilizes shadowgraph to detect the time evolution of the drop's contour. The experimental videos are recorded with a high-speed camera and it is later post-processed and analyzed to obtain the spreading radius and instantaneous contact angle. The closed chamber of the high-pressure unit is pressurized first to the desired limit, and after the pressure inside is stabilized, I use the manual dosing system to generate and deposit the drop. From the results of the experiment, we observe that the drop achieves a more spherical shape in higher surrounding pressure as compared to atmospheric conditions. In addition, we witness a reduction in spreading radius and a subsequent increase in the contact angle, from which we conclude that the wettability of the substrate reduces with increasing surrounding pressure. Non-dimensional plots of the evolution of the spreading radius are obtained to eliminate the variation of initial drop volume that is associated with a manual dosage. From the non-dimensional radius versus time plot for one experimental liquid, here that is called N35, we observe a decrease in spreading velocity due to increased viscous dissipation at the contact line when the surrounding pressure is raised. Additionally, a high ambient pressure decreases the switchover time from the inertial to viscous regime. Furthermore, increased pressure causes a notable change in wettability, which is characterized by the contact angle during the later stages of wetting. As I have mentioned in the beginning, the findings of this study can be applied to better the understanding of the spreading mechanics of supercritical carbon dioxide in deep porous reservoirs used for curbing atmospheric emissions. Injecting the carbon dioxide at high pressure will limit the degree of lateral spreading inside the reservoir, which will subsequently lower the risk of leakage to overlying strata or shallow water formations. As a result, the trapping efficiency will likely increase, ensuring the sequestrated carbon dioxide remain trapped for years on end. In the future, we plan to further analyze this unique spreading behavior at the early time using different surrounding temperatures. Additionally, we will conduct molecular dynamic simulation while considering pressure effects to understand this phenomena at the nanoscale. Thank you very much for listening.